Well, ladies,
I haven't
without
seen
further
that.
ado, I think we should go ahead and start. I try my best to be a good steward of people's time, especially on a Saturday. I want to welcome our girls back for cycle two. There should be a couple more coming in, so hopefully they'll trickle in. But welcome back to She Can STEM Academy for our second cycle. Just for Katie and Bill's information, the ladies that you see on the screen, they have completed cycle one. So they have gone through 8 weeks of where we brought STEM to them. They actually have seen and interacted and a variety of female STEM speakers. And now they are interested in actually going to a facility to see what happens at a facility. So that's why they're here today. So I am happy. I'm always so excited on Saturday mornings to be hanging out, learning about STEM. They know that I don't have any background in STEM, but I am so intrigued by it. And I'm happy that they are interested and they chose to come back to the second cycle. And just a quick overview of our speakers today, ladies. I talked to them yesterday and I thought about our conversation. From the time I hung up with them, I am excited that they're going to share some really interesting things with you. But we have Katie Bethay and Bill Renard, and they are from Oak Ridge Laboratory, located in Tennessee. So they're all the way in Tennessee, and we're here in Hampton Roads. I think Jalea is in Maryland. I think Kyla, are you in Hampton? Now, where are you, Kyla?
Me?
Yeah, you.
Oh, I'm in Williamsburg.
Are you in Suffolk?
No,
What's it?
Williamsburg.
Williamsburg, that's right. Okay, okay. I knew it was not around here. So we are joined by so many all over. Bill Renard is an HPC engineer. That sounds really hard, right? But he is a leader at the Oak Ridge Leadership Computing Facility. And this facility is the home of the largest supercomputer, and it's called the Summit. And we're going to get to know the Summit a little bit better today. He has over 20 years experience providing support to users who use this supercomputer. Katie Bethay is a facilities communication and outreach leader. She coordinates a team of writers and artists and web developers. Oak Ridge National Laboratory is the largest multi-program laboratory in the United States, out of the 17 national laboratories. Among many other exciting work facilities and resources, the lab is the home to the nation's fastest supercomputer. So without further ado, they have so many other accolades I could definitely tell you about, but I will let them just show you what they do. So I'll turn it over to Katie and Bill.
Thanks so much. It's really nice to see you guys. I'm Katie. I am actually from Hampton Roads also. I went to Hines Middle School and Ferguson High School that's not there anymore. So it's really nice to see some folks from my home. Let me tell you some things that we're going to talk about today. So in school, I studied English as my undergrad degree, and then I also studied biology. And as a English and biology major, I spent a lot of time talking about communicating science and helping people understand science. And so I get to work with folks like Bill and help make their science accessible to everybody. So as a what did you say, Katina, as a STEM head, that I think I could qualify. Just really excited about science and how it affects our everyday lives, and getting to help other folks get excited about it. I've been at Oak Ridge National Laboratory for about 6 years, and it is a pretty exciting place. We are, as you already said, we are the largest of the 17 national laboratories. We are a Department of Energy laboratory, and so we're studying all things related to energy. materials that can be used to in energy production, energy storage. We're interested in nuclear power. We're interested in just anything that you could imagine that's related to energy. Our lab is touching on that. And one super cool thing that we have at our lab is really, really big instruments. And so in your labs at school, I'm sure you have some scientific instruments. You have microscopes, you have Bunsen burners, you have beakers, you have the different tools that you use in science. And our scientists at Oak Ridge have all of those same tools. And some of our tools are really, really big. We have the spallation neutron source, which is like a super huge microscope. It lets scientists see particles interacting at the molecular level, the teeny tiniest level. They can see the particles interacting. And then we also have what Bill and I are here to talk about. We have the world's fastest, or the nation's fastest supercomputer called Summit. And so let me share my screen and I'll zoom in a little bit and show you where we are. Just one second. Here we go. Okay, so this is kind of an artist rendering of our lab and what it looks like. And this is one part of the lab. It's very much like a college campus. There's a bunch of offices and a bunch of facilities. We've got a bunch of infrastructure stuff because we've got to keep the power on. We've got to keep the air conditioning running. And then we have a bunch of really cool research facilities. So this is our computer facility. And this is a quick view into the Summit supercomputer. Summit is, or a supercomputer, that's where we can kind of start, is a tool that we can use to see or to do experiments that are too big for a laboratory, too dangerous for a laboratory. If there's a material you want to work with that you don't want to blow the building up, maybe something that's too complicated for a laboratory, like where we have to understand a really complicated thing before we could really touch it, or sometimes too expensive. There's materials, or there's things we would want to work with that it would be very wasteful to do a laboratory experiment. And so our researchers can use the supercomputer to study those things. And they do that using modeling and simulation. They also do really big data crunching, like they take lots and lots of information and they can find patterns in that information. And so this is kind of the entrance to our facility. It looks pretty boring. It's just a hallway, which we really miss because we don't get to go there right now. But we have this big construction project. So I'll peek in this window and you can see this big construction project through that window is our next big supercomputer. And you can see a bunch of empty walls and scaffolding and stuff. That supercomputer is being built right now. But this is our control room, and this is where the guys can monitor what's happening all day long in the computer, on the computer. They can look for if there's a water leak or if there's power issues. They're watching that 24/7. So the folks in there, let's see if I can jump easily. Here we go. The folks in there are often technical, like computer scientists, but more on the IT side. Like they're interested in computer networking and they have those kinds of backgrounds. Okay, so here we're gonna walk into Summit and kind of can make you seasick. So hold on tight, everybody. So I'm going to hand over to Bill so he can tell you some other details. But let me just introduce you to what you're seeing here. So a supercomputer. We're all looking at this call right now on a device of some sort that has computer chips. I'm on my laptop. Some of you guys might be on an iPad or another tablet. But all of those devices are the same. They have computer components. So if you imagine your laptop or your iPad times 5,000 or more, that's what you're looking at right here. That supercomputer in each cabinet is 18 or more computers. And so when we line them all up together and we connect them with really, really high speed connections, we can we can solve a problem way, way faster than we could with one computer. And so we call that parallel computing. We distribute the problem across all of those computers. And and um, to make that happen, we have a lot of infrastructure. So you look up at the ceiling, you see water tubes and you see power lines and you see a lot of hoses and stuff. That's what helps these computers run. So if you think about your laptop, have you ever heard the fan running and it kind of can get a little bit loud, or if your laptop gets hot when you're holding it? Imagine the same thing is happening here. These computers are all getting pretty hot, and so we have to take the heat away. So we have to have, in this case, we use water to take the heat away, and then we have power. Obviously, we have to power them. We have networking cables. There's 180 miles worth of networking cables. So that's for here in Tennessee. That's from Knoxville to Nashville. Where you guys are, that's probably Hampton Roads to DC, about same distance.
New York to Boston.
New York to Boston, that's a good one too, Bill. It's a lot of wire, and that's what keeps the information flowing. You've got to make the data move. Let's see. So Bill, I'm gonna hand it over to you and let you kind of walk through the room and point out some other details. But I think the point I want to come back to is why do we need this supercomputer? So we think I can give you some examples after Bill takes you for a little walk through here of what we use it for. But the answer there is just dream up any scientific problem you can think of, and we've probably worked on it. So let me. Bill, actually, I'll keep control if you don't mind, and if you want to point me to where you want to go.
Okay, yeah,
Okay.
where you have it is really good for right now. Thanks everybody for being here. Just a little quick a bit kind of where I've come from, what brought me here. My degree is in computer science, so I was interested in computers, when I was younger, and strangely enough, never had one at home really until I was very late in my high school career. Used some of the ones at school, and you probably wouldn't recognize what we had as computers at school. When I was in high school, they were very, very basic compared to ones that we have today. But I went to Mississippi State, got my degree in computer science, was working at a Department of Defense supercomputer center for a few years, almost 5 years, and then have been up here at Oak Ridge since about 2005. So always doing the same thing. And yeah, they said earlier my title was HPC engineer. What does that mean? The work that I do, I'm in the support group for the users that use these computers. So everybody has trouble using a computer. Sometimes you get an error message that you don't understand. Something's not working the way you think it should. So you go ask a question, and maybe you type that question in Google and find your answer. Or sometimes you might email somebody or call somebody to get an answer. And that's my role, is helping these scientists find these answers. And the thing that's, I think, a little bit frustrating about it, and also a little bit fun about it, is we can't always just go Google and figure out the answer, because a lot of times these are very unique computers. Nobody has had this problem before, so there's not a solution on the internet to go find. So we have to understand how the computers are working, and a little bit of how the user's working and how users think, so that we can figure things out. On to the part that's far more interesting than me, the computer itself. We're looking at Summit, and you know, a lot of times you'll hear people say, oh, computers used to take up a whole room. And that's true. And something that's as powerful as the laptop that I'm using right now, yes, used to take up an entire room, and now it takes up, you know, a couple of square feet on my desk. Um, but there are still computers that take up a whole room, and you're looking at one of them. Summit is about 5,000 square feet. That's about the size of two tennis courts. So it is certainly a very large computer. If you'll hold it, can you turn it, Katie, so that we're looking down one of the aisles? We almost had it. Yeah, that's great. Um, so this is just cabinet after cabinet. Summit has about 4,600 what we call nodes. You can think of a node as an individual computer. It's got a little bit of storage on it. The nodes on Summit have 512 gigabytes of memory, and they have two 22 core processors. So my laptop is kind of old. I think it's either a dual core or a quad core processor. I think it's dual core. It's pretty old. Newer ones probably have more than that. My own home computer, I just upgraded, and it's an 8-core processor. These nodes have two 22-core processors, so that's a lot of processing power. But the really interesting part about it is that's not where they get all of their computing ability from. They also have graphics processors, the same kind of chip that runs a display, runs your monitor. Scientists use for actually doing calculations. And how that came to happen was really people just playing around with their own computers and figuring out you could repurpose this hardware. And instead of having it create some graphical image, you could have it do mathematical calculations for you. And without getting too much into it, it turns out the kind of mathematical calculations that show up in a lot of scientific computing, the way you do those calculations and the kind of work you have to do is really similar to the work that you have to do for graphics. Basically, it's doing the same operation over and over and over again over a huge amount of data. So if you think of your monitor or your display screen, there's a couple of million little pixels on there that have to keep getting updated. And for us to see smooth motion, they have to get updated about 30 times a second, so at least. So that's a lot of calculations that have to happen. And it just happens that that works well for scientific computing too. So you see all of these cabinets. Each one of these cabinets has 18 of these nodes stacked up inside it. And here, and I'm pointing at my screen, I know that doesn't that doesn't translate very well. If you look at the top, you can see these black tubes that are coming down into each cabinet. That's perfect. Leave it right there. That's the power cable. So that cable is about as big around, maybe a little bit bigger than the hose at the gasoline pump. So it's pretty big. It's carrying, if you have heard of or familiar with kind of power and how we talk about power, it's a 480 volt, 200 amp connection going, 100 amp, going into each cabinet. That's about the same amount of power that goes into a standard house. So each of those cabinets you can think of as a house worth of electricity. Over to the left side of the screen, you see the backs of the cabinet. So these cabinets are set up front to front and back to back. So there, we're looking at the back of a cabinet. If you look up at the top, you see there are two hoses about the same size that are going into each cabinet. Now, in this case, those are not carrying electricity, they're carrying water. So all of the components in these computers create so much heat. I thought about this just in passing since I've been playing with my own computer. I have the old component sitting here. So this is down under here somewhere is the processor, and you see what we call a heat sink, this metal thing with all these fins, and there's a fan on top of it. That's good enough to keep my computer cool, the one I use in my house. It wouldn't work for something like Summit. So instead of having that big fan sitting on top of each processor, it really looks just like a thin piece of copper, but that thin piece of copper has water moving through it. So water is a very, very good carrier of heat. When you get some water hot, it stays hot for a long time. When it gets cold outside, it can be below freezing, and a lake isn't frozen solid because that water still holds on to some of the heat that it got. So it's really good thermally for this kind of stuff. So those hoses are carrying that water into the cabinet. There you can see one of the nodes. That's what it looks like inside. You see the tubes are what's actually carrying the water around. Those little pieces of copper that you see are what we call cold plates. That's where the water is flowing to go through the system to keep everything cool. So Katie talked a little bit about scientists using this whole computer for solving these really challenging problems. And that's really what defines a supercomputer. So it's not that the processors or the graphics chips in this computer are so much faster than somebody could have in a home computer. It would be a kind of expensive. It would be a high-end computer, but somebody could certainly have these kind of components in their home computer. So it's not that the processor is so much faster. What makes it a supercomputer is there's so many processors. And a former coworker of mine had a really good example that I think translates well. Think if you had thousands and thousands of various Lego bricks that were spread around, and you needed to pick those up and sort them. Could one person do that? Absolutely. Would it be faster if 50 people did that? Yeah, absolutely. And that's really the approach that supercomputing is taking these very challenging problems, modeling the Earth's climate, modeling a star as it explodes as a supernova, modeling earthquakes that have billions and billions of calculations that need to be performed. So you let each computer do a little part of the calculation. Now, at some point, what the work that one computer has been doing has information that another computer needs. You know, at some point, if you're calculating, an earthquake moving through the Earth, you've finished your part of the screen of the Earth, and you need some information from the next part of the Earth that your other neighbor computer is modeling. So they have to talk to each other, and that's where that network that Katie mentioned comes in. The one that's got the 180 whatever miles of fiber connecting everything together. If you remember the earlier images, those yellow trays that were up at the top, those are carrying these huge bundles of fiber optic cable that connect everything together to let all these computers talk to each other. The green and blue that you see at the top of the screen there are water pipes that are carrying all of that water that's needed for the cooling. So it's amazing how much infrastructure has to go in to this computer to allow it to work and allow it to work really efficiently. The other thing we have there on the left side of the screen, you see some similar looking cabinets. Those are actually holding all of the disks for this computer. So I mentioned a node was kind of like a standalone computer, and it is, and it's got a little bit of storage that it can use, but it's not really where the hard disk would be if you think of how your typical laptop is. So the disk is kind of separated off. It's over in these other cabinets. And just like we put a bunch of nodes together to make a powerful computer and think of it as one big computer, we put a bunch of individual disks together and use some special software and some special hardware to make it look like one really big storage area. So that storage area is about 30,000 individual disks that are put together. So yeah, I did say 30, 30, 30. So a really huge amount of storage. That's about 250 petabytes of storage. Now, you probably haven't heard of a petabyte before. That's 250 million gigabytes. So 250 and then 15 zeros. So an enormous amount. I can't remember. Oh, I
70
did the
years.
math and I can't remember what it is, how many years of Netflix that is, but it's hundreds of,
It's 70 years.
okay. Is that
You could
70
watch
years
a movie.
of 4K?
Yep.
Okay,
Or HD.
okay, that's 70 years of really high quality video. That's a lot. If you look at, I think some of the lower stuff, you can get into hundreds of years worth of video. So it's really amazing. The other thing I'll mention, we kept talking about Summit being the fastest, the fastest. What does that really mean? We're talking about how quickly it could do a number of calculations, or basically how many calculations it can perform. So if you study computers, if you look at how the computer chips actually work, the way they do math changes based on what kind of numbers they're using. So the way we do math, if a number has a decimal point or if it doesn't. So if we think of 123 times 45 versus 1.23 times 4.5. If I get out a piece of paper and I do that calculation, I do it exactly the same way. The only difference is at the end, I know some rules that I learned 30 whatever years ago that tell me where to put that decimal point when I'm done. Computers do math with and without decimal points differently. And if you think about it, are you familiar with scientific notation where you have like 1.2 times 10 to the fifth power? Well, computers actually store numbers similar to that, basically in a binary version of that. And what that lets them do is represent a huge range of numbers. And if you really use your imagination, where the decimal point is in any given number can float around to make that number bigger or smaller. So those are called floating point numbers. So kind of a weird term, but that's why we call them floating point numbers. And floating point numbers are the ones that are of interest for scientists because they can represent so many different range of values. And that's also where we get the number to say how powerful a supercomputer is how many floating point operations per second it can perform. And that's a lot of words to say. So, this is the world of science and the world of the government. So we like shortening things and making acronyms. So we call it, instead of floating point operations per second, we call it flops. So it kind of sounds funny, but we call it flops. So if you look at what Summit can do, how many operations it can perform, it is about 200 petaflops. So 200 quadrillion operations per second. 200, basically a 2 and then 17 zeros, calculations per second. 200 million billion. That is, it's hard to understand how big that number is. If you think of a Post-it note, if you had that many Post-it notes, you could cover the entire Earth a couple of times and then cover the moon a few times with that many Post-it notes. It's just an enormous number. Katie showed you the construction area earlier, which is where we're getting ready for the next computer we have that'll be called Frontier, that we've already been planning for Frontier for a couple of years, and it's ongoing, and hopefully it'll be here soon. That system is going to be 1 and change exaflops. So a 1 and 18 zeros calculations per second. So that's when we get to a number called quintillion. So 1 quintillion calculations, or more than that, 1.5, something like that. Quintillion calculations per second. So again, really hard to understand how big these numbers are. But the reason when it gets here, it might be the most powerful computer in the world, and that'll be cool. Summit used to be the most powerful computer in the world, but that's not why we're making these computers. That's not why we have computers that are that powerful. The reason we have computers that are that powerful is because the real world that all of these scientists that are using the computers are trying to model is really, really complex. If you think of modeling the climate, really every little molecule in the atmosphere has some part in that. Now, is the difference between whatever is on this fingertip and this fingertip going to make a big difference in our climate? No, not really. But when you spread over a few miles, maybe so. And there's lots of miles of atmosphere that need to be modeled and lots of calculations. So it's to the point where there are some problems in science that a scientist might like to do, and they know how to write the program to do it, and they know how to get the data to do it, but they can't run it. Because if they tried to run it, it would take, possibly days or years to run one simulation on a less powerful computer. So they need more and more powerful computers so they can get the answer in a good amount of time. This is just an example. We don't have such a model, but imagine there was a model that could predict with 100% accuracy the weather forecast for the next 3 days, but it takes 4 days to run. That's not helpful. But a more and more powerful computer that can make it run faster, maybe in a few hours, then there's a lot of benefit to that. Katie, go ahead.
I have a question before Katie starts. So Bill, I
I
have
was gonna
two
say-
questions actually.
Yeah, go ahead.
You mentioned that Frontier is on its way. Why do we need a faster run? Why do we need Frontier? And my second question, if I'm a scientist here in Hampton Roads and I am studying the weather, how can I use the supercomputer?
Okay, two great questions. The first one, if we have such a powerful computer, why do we need more powerful ones? Part of it goes to there are still things we want to do that, as powerful as Summit is, we need something more powerful to give us these greater insights into materials or energy research or whatever the case may be. And, as we look at it nationwide, and what's the Department of Energy's interest in having such powerful systems? Scientific knowledge and supercomputing as part of what gathers that body of scientific knowledge is really important for the world and for the nation to stay, at the top of these scientific areas. How would a scientist use the computer? Really good question. We have probably 1,000 or so users that have accounts on the system. Maybe it's a little more than 1,000 and a little less than 1,000 actually log in and use it at some point. The way somebody is able to do that, we have most of the time that we give out is through what we call a call for proposals. So every year, it's actually 2 times a year, this announcement goes out that says, hey, here's this huge computer that you can use to do great science. Here's how you apply to get time on it. And the scientists will write up the kind of science they want to do, how they intend to use the computer to do that. That gets reviewed. And a handful of those projects are awarded, the ability to use the computer. Now, it's normally one or maybe a couple of people that actually generate that proposal. It could be many, many people that actually do that work. So the way most scientists get on the computer is they're working with somebody who has one of those proposals. So they apply to us and say, hey, I would like an account to do this kind of research, and I'm working with Dr. whoever. And we'll look through and make sure everything is right and there's no problems with giving them an account, and the doctor whoever says, yep, let them use my project. And then we give them the right to connect. Now, an interesting thing that kind of tags on to that, a lot of times when we have tours, people will ask, where's the monitor? Where's the keyboard and whatever for Summit? And there's really not one. The monitor and the keyboard are whatever is sitting in front of the user. So when you go look at a website, let's not even talk about a website. We're in a Zoom meeting right now. There is some computer somewhere that Zoom owns that is hosting this meeting, that has the software that we're all connecting through and using, but we're all using our individual computers or tablets or whatever to do that. That's exactly the kind of approach that a scientist uses to use Summit. They connect from their computer to Summit. It's actually, oh yeah, I do have it right here. I can actually connect to Summit with that. So it seems odd, but I have a piece of software on my cell phone that I could log into Summit with. So that's how they actually go about using it. So most of our scientists never set foot on Oak Ridge National Lab property. They never visit Tennessee. They use it from wherever they are in the United States or internationally. We do have some users that are outside the US as well that are collaborating on different projects.
Okay, thank you.
Of course, nowadays, most of the staff doesn't set foot on lab property, but maybe we'll get past COVID and that'll change.
We miss being there. We have a great question in the chat, but it connects to what I was about to say. The question is, what's the hardest problem that Summit has ever helped solve so far? This year, or in 2020, we had the exciting opportunity to be able to study COVID-related problems. And in February, so before you and I were even really thinking about this, we had some researchers that put their heads together and they said, we're starting to read about this new coronavirus, and this might be a problem. And so they got together and they took what they knew to be the protein model, and they said that the way that protein works, that the protein of the virus is that there's this spike, and that's where binding happens basically. And what if we took all the known medications, drugs, vitamins, just all these known compounds, and we compared their structure to that spike protein and see if any of them can prevent it from binding and making people sick. And so they took Summit and they took that model of the spike protein, and then they took all of these compounds and they compared them. They literally, like, if you could watch it happen, like like the Matrix, like they're just connecting, and they came up with 70 target compounds that could possibly be used to treat COVID. And they took that information and then they worked with experimentalists. There's some researchers who actually had the virus in a laboratory, and they were able to take their recommendations and narrow it down to some treatments. And that helped influence some of the treatments that the doctors ended up using have ended up using with patients. Similarly, we had a group that refined the model of the COVID virus using Summit. And that's really important because of all these other researchers around the world who need the most accurate information. So the fact that Summit played any minor role in better understanding COVID-19 is really exciting to us. But that we were able to adapt and respond quickly to that big international problem is pretty cool. And that ties into your question of why we need a faster computer. One run of that big data set of drugs took them maybe 24 hours. It would have taken 1 to 2 months on other leading systems. Those are other fast computers. So the fact that as the fastest one in the nation, we did it in 1 day is amazing. So imagine what we could do with the next fastest, with Frontier. Could we do it in an hour? Could we do it in a short afternoon? That'd be pretty exciting. So being able to get to the solution faster is really the goal. Sorry, Bill, I'll hand it back to you if you have more things you want to say.
No, that's a great example. And even though, yeah, they narrowed it down to 70, and that's still a lot that you have to study in the lab, but that's from how many thousands of candidates did they start with? So that's really how supercomputing can help us. And a little on some of the there we see some of the networking that connects everything together. So you see all of the dark blue and light blue and the black cables that are there kind of near the top, middle top part of the screen. Those are all network cables. They're where they go to and exactly what they're doing is slightly different based on the size of the cable and connecting everything, but they're all part of that network. Now, personally, and I watched them as we were installing everything, and just one of the things that just blows my mind and just I don't know, if you look over on the on the left side of that cabinet, just to the left of the circle, you see that big bundle of fiber. And if you look down at the bottom, you see where that spreads out and connects into all the switches. And if you look really closely, you see a bunch of labels. All of those cables have to be labeled when they connect at both ends. So you think, and this is one of several cabinets that looks like this. I can't imagine having to do all of those little bitty labels. But that's one of the things that's important. If there's a problem with a connection, you have to have that thing labeled on both sides, or you will never trace it down in that huge bundle.
So Bill,
So
that's interesting you say that, Bill, because as you were talking, I'm looking at this room, I'm looking at this supercomputer saying there's a lot of different jobs in here. So someone has to maintain the computer. Oh my gosh.
There absolutely are.
Who makes sure that this space is safe and clean? And I mean, there's so many jobs in this room.
Absolutely. Now, one question we get a lot of times, where the computer is not what you would hear called a clean room. So there's not putting on some special clothing to walk in there. You walk in whatever you wore right off the street. So it's not we're not worried about there being absolutely no dust in there. Now that would be a concern where they actually manufacture the microprocessors and things like that. But for us, it doesn't matter. I mean, we want it clean, but it doesn't have to be, immaculate. But absolutely, we look at the jobs that are necessary to do this. Now, the work that is actually done on the computers, these are, PhDs in many different fields of science and whatever. You've got people and mathematicians and things like that. The people that are running the systems that are supporting them don't know the science, but they understand computers, so they've gone into that study. But this thing is powered with an incredible amount of electricity, megawatts of power. That the Summit supercomputer, the total power capability going to it is about 10 megawatts. When it was running a benchmark, it was kind of close to using 10 megawatts of power. If you remember way back at the beginning of this tour, that shot of the whole campus, in the late 90s, the entire Oak Ridge National Laboratory was using 20 megawatts. Summit can use 10. So that's a lot of electricians to keep all of this working, keep the power to the building and within the building working. Uh, we look at the top of the screen right there, those big water pipes. You see the black ones there with the kind of the green labels on them. And you also see the blue and green pipes, just a couple of different types of pipes because they're doing different things. There's a lot of water. There's a swimming pool on top of the supercomputer. Basically, if you look at all the water in all those pipes, there's got to be plumbers to make sure those pipes are assembled correctly and they're not leaking, because we don't want water to leak on our supercomputer. There's all kinds of jobs that make this computer work. If we don't have the scientist, then the computer's not doing anything useful. But if we don't have the electrician and the plumber, the computer's not doing science. So all kinds of fields in there.
Yeah, and I'm thinking there's engineering because someone made those pipes a certain way to fit into that space.
Exactly. Those green and blue
that's
pipes are plastic.
Right?
And somebody had to figure out how to make that work, how to mold it right, how to fuse two pieces of it together so that it doesn't leak. You've had the engineering of designing the chips itself, so the chips themselves. So all kind of engineering.
One of the that's one of the reasons I landed here on this energy plant that supports the system, because that's not something we often think about, but the infrastructure here. So we have electrical engineers, we have mechanical engineers, like that whole crew that has to understand what a computer does in order to support it, in order to design such a cool support space. Another interesting group that you guys might have heard about is like cybersecurity. And we, Bill mentioned that you can access Summit from anywhere using our secure access. We give people access, but we have to be really careful. We don't want people hacking into Summit. We don't want somebody being malicious and putting a virus on our machine. You don't want one on your laptop or on your phone. So cybersecurity is really, really important. The other thing, all of the business roles that support the lab are really important. We have accountants, and we have folks that are that do our procurement, that buy the stuff we need and make sure that things are done legally. We have communicators like me and my team. I have writers, I have artists, I have folks who build websites. So if you're really into building websites, there's people that work with Bill that write software. So if you're interested in coding, I'm sure that that you guys have had a little introduction to coding, and there is a lot of opportunity there.
I think there's
the other thing. Go ahead.
Oh yeah, I was going to say that there's another thing that just kind of occurred to me as we're talking about the different jobs, and as we've looked at some of this, just looking at some of the building and structural engineering that goes into it. The place where we were just looking at Summit, when I started working at the lab in 2005, that place was called Outside. So that entire building has been built in the time that I've been here. So fitting that building in between two other buildings and making sure everything works right. The other thing that's been kind of interesting, you all don't know it, but you have walked through my office twice in this virtual tour. Because right back where we just were looking at the central energy plant used to be offices, and one of them used to be mine. The little walkway that we just went past, the little walkway where you go to Summit, that little short hallway, that used to be my office. Then my office got completely removed, turned into a hallway to connect to this new part of the building. So, somebody has to do that stuff as well. So all kinds of very different, interesting jobs touching many different scientific and other disciplines. And yeah, there's some of them that I'm very thankful that there's people there to do, because I do not need to be working with high voltage electricity. I would hurt myself really badly. I have no desire to be working on the accounting side of stuff. So it's important to have people that really love that area of the work to, so that we can function as a facility.
So before we come to a close, I want
And I think
to just, I'm sorry, Katie. I was just going to say, before we come to a close, I want the girls to know
yeah,
that,
I was just going to make the point about,
go ahead. Go ahead, Katie.
I think I have a delay. I'm sorry.
That's okay. Go ahead.
The in computing or in all fields of science, to computing in all fields of science is really valuable. So having that background is something to consider if you are looking into a career in science, making the investment into computing.
Thank you, Katie. I was just going to say some of the same things. I just wanted the girls to know before we close. It's important to look at STEM differently. We have named about 5 or 6 jobs just in this one presentation today. And young ladies, it doesn't have to be, it can be you. It can definitely be you to do these types of jobs. So I want you to really look at STEM very differently. This may be something that you didn't know about, didn't hear about in your classroom. That's really the whole purpose of today. And I'm so thrilled that we named about 4 or 5, I'm sure there's more, of positions that you can do in a laboratory. Katie, are you frozen?
I think so. Can you hear me?
I can hear you, yes.
Okay, good. Yeah, it feels like everybody else is frozen. I was going to share the link for you guys to explore those tours that we showed, so that you can look around on your own, and you can send us questions, or if there's anything that you wanted to know more about, we would love to follow up with you guys.
Wonderful. I had to get my battery because I was going low. I kept wondering why my screen looked dark.
And yeah, as we've covered, there's lots of interesting science that's done. So, that computing plays a part in so many different areas of science. So, those, kind of coding opportunities that you can get, and little exercises like that is really helpful in all different areas. And, yeah, there's a lot of really interesting stuff that's done, and stuff that, even I still learn every day on the job, learn more about science just from the scientists that we have. So it's always that continuous learning is really important.
Thank you. Katie, are you able to put those links in the chat? Is that, oh, perfect.
We're thinking alike.
So ladies, if you're interested in learning more about the laboratory and seeing other parts of the laboratory, I think some of these links that Katie's dropping into the chat, please feel free to click on those and save those in your, I guess you can bookmark them so you can go back and see them later. Do we have any questions? I'll definitely be checking these links out myself.
It looks like Katie may be typing some of the other ones in now. That first one is just the computing, but I know the lab has done several tours with that same technology for some of the, the lab. Oak Ridge isn't just supercomputing. So there's a lot of work in other areas as well. I think one of the virtual tours is what Katie mentioned earlier, the spallation neutron source, which is, it's a way of looking at materials. Instead of using light to bounce off of a material and make discoveries, it's using neutrons to bounce off of materials and make discoveries. So that's way over my head, but it's really cool. There's, I think one of them is the graphite reactor. So Oak Ridge is home to the second nuclear reactor that was built. The first one was built at the University of Chicago under the football, or yeah, I think it was University of Chicago, under the football stadium, kind of as a test to see if, this theory would work, and it did. And the one at Oak Ridge was the next one that was built. And of course, it's not used anymore, but it's still there as a historic landmark, as one of the tours, and some of the other stuff as well. All kinds of different science done at the lab.
Nice. Any questions from our participants? Let me ask you a question. So there's a lot of information that was shared today. Some may have gone over your head, but did anything that was discussed spark an interest? You raise your hand. I raise my hand.
Thanks.
Jalay, I'm going to pick on Jalay because I know, Jalay, are you interested in cyber? Am I remembering that correctly?
I'm interested in more like, I'm interested, no, not really.
No. Tell me remind me, what are you interested in?
I'm interested in, like actually experimenting with like potions and stuff.
Okay.
Cool.
Okay, cool.
Yeah.
Okay.
We have a lot of chemists
not
at
talking
the
cyber.
lab.
I'm sorry, Katie?
We have a lot of chemists at the lab who are doing all kinds of wet lab experiments.
Okay.
They're mixing materials.
Mm-hmm. So Jalay, you want to see things blow up.
Yes, very much.
I've heard one of my colleagues at work that is actually, many of my colleagues at work are astrophysicists. I don't know why. We have several people in my group that are, and some others at the lab. And, one of them jokes a lot because what a lot of astrophysics is modeling stars blowing up. But that's also something that's interesting for all of us, because, just an interesting aside, one of the things that I've learned at the lab, stars blowing up is a really good thing, because one of the things that does for us is it gives us oxygen, because stars form a lot of elements as they go through their life. And when they explode, that's where those elements get sent through the universe. So one of the reasons that's studied, and one of the reasons that's of interest for using these powerful supercomputers, is understanding, where a lot of these elements crucial for life come from. And it's from stars. That's just one of those interesting things you pick up in, working and listening to these scientists.
Now we have Leah who's on the call. Leah is interested in weather, tornadoes. She knows all things about tornadoes.
Awesome.
And we can't get her started because she will go on and on and on. But I can definitely see this laboratory also being of use in studying maybe why tornadoes form or why they go a certain way, or yeah.
So atmospheric science is where you want to go, and studying how complicated the atmosphere is, and what causes those disturbances that end up being tornadoes or hurricanes or other things. And Bill, he's very interested in weather. Yes.
Nice.
Actually, I'm not used to hurricanes. I'm used to tornadoes. That's the point.
Gotcha. All right.
We have someone interested in tsunamis. Okay.
Very
Wonderful.
cool.
Well, I want to say thank you.
Yeah.
You have a question, Leah?
Sure. Let me ask you something. If tornadoes have wind speeds over 200 miles per hour, and that EM3 tornado have wind speeds from 136 to 165 miles per hour, so why don't that EM3 tornado get higher ratings?
I don't know.
Why
That's a
don't
good
that
question.
tornado get a higher rating?
Yeah, good question.
Ever since that so-called Oklahoma EM3 that happened in midnight 2016.
So I know a lot
that
of
type of monster.
I know a lot of weather folks who I could recommend to present to you guys if you would like to get some connections.
Yeah, absolutely. One of our closing speaker for the other academy in March, she's actually going to do this one as well at the end. But she is a meteorologist, and she is, oh my gosh, so passionate about it. So I can't wait for
Perfect.
Leah to definitely meet this particular.
That's what I wanted to do.
Yeah, don't get Leah started. We'll be here all day talking about the speeds of tornadoes.
I love it.
Well, and that's also cool for me as
I'm
well,
just used
because
to those type of weather.
I'm sorry, I was saying that's also kind of interest to me
Well,
as
actually,
well.
it's
Uh,
funny. That's
talk-
really scared.
I'm sorry, I may have been talking on somebody. I kind of have an interest in that as well, because a lot of now there's operational meteorology and the people that work for the Weather Service that are different from the people we see on television. But a lot of the people we see on television kind of have I have a common bond with them, because about a third of them went to or got their degree from the college that I went to. So, because it's got a very big broadcast meteorology program. So that's always kind of interesting. But yeah, I've always kind of had the interest in not so much in that part of it. I'm not exactly television material, but yeah, that's always been an interest of mine. I think there's probably only 3 of us on here that would get this reference, but when I was in elementary school, one of my nicknames was Billard Scott.
Miller Scott.
If
Okay.
if you remember the old
Uh-huh.
guy Willard Scott,
Willard
so
Scott,
we would
yes.
make it a B, so Billard.
Yes, I do remember him. Yes. Well, thank you all. Again, when I talked with you yesterday, I knew that this was going to be interesting. I hope, ladies, that something that was said will spark you to go do a little bit more research, and do some things on your own to perhaps spark some interest. We will meet again next week. We'll be highlighting a wind farm, which I'm really interested in that. So we'll take a look at wind farms and wind turbines and how that impacts energy as well. So thank you to our speakers. Thank you. Kyla Stewart is our intern. She is an engineering intern from Top Water Community College, so she's hanging out with us as well. Thank you for just spending your Saturday morning or afternoon, I should say, with us. And we look forward to seeing you again at She Can STEM Academy next week. All
Thanks so
right.
much. Bye, guys.
Bye-bye.
Bye, Ms. Barnes.
Bye-bye.